Thank you. If you'd like to take your seats, if you're not already, we're for our final session on engineering, which is a hardcore session this is. I can't promise to understand everything that's presented in this section, but I should do my best. Welcome. Thank you for coming. This is Professor Dr. Stefan Vöth. Is that right? Vöth. Vöth. Okay. Yeah. Okay. This is going to be a recurring theme in this session. Me trying to get. I'm very bad at names. And obviously Professor. And the Technische Hochschule. Oh, I'm not even. Do you want to say where you work?
Georg Agricola. That's a former scientist in Germany, like Leonardo da Vinci. So he covered several disciplines, and he gave the name to our institution.
Excellent. Welcome, and thank you very much. Over to you.
Thank you. So thank you for this opportunity to present. Dark agenda. Now it works. This is more or less a revisit of my presentation last year. I told you last year that I'm not an expert on lifts. I just heard maybe there are some other non-experts of lifts here in this room as well. But I'm working on cranes, which is also lifting equipment. And considering cranes, we use buffers. Yeah? As you can see on this picture, no, you can't see. There. I do not exactly understand. We will manage it. And
so this is forward?
Yes.
This is back?
Exactly.
And this turns it off?
Like I to operate. Okay, my fingers are not that small. Okay, we have those plastic buffers they might use. But we also have such hydraulic buffers. And last year I told some aspects about hydraulic buffers and especially calculation of such buffers. And I remember it was you, Rory Smith, asking me some question about it related to lifts, and I wasn't able to answer. And this was annoying to me. And I started to read some standards, EN 8120, and the requirements on buffers in lifts. And I've done some more calculation, and today I want to give you maybe the answer on your question. Yeah, that's the idea. Basically, those hydraulic buffers work quite easily. You have a throttle, you have some oil pressing through the throttle, some pressure occurs and produces force on the piston. And this force, in your case, is used to break down the car in an emergency case. Yeah. The idea at breaking down is to produce some constant deceleration, which leads against time to a linear decrease. Is there a pointer? Ah, yeah. Linear decrease of speed. And maybe you can also see pictures like on the left side against the position of the piston, where the deceleration is not linear anymore. You can have different approaches. Your car has a certain energy to be dissipated during this process. And this is the surface you can see here in these diagrams. And you have the choice. Either you break down with a large force over small stroke, or smaller forces across a higher stroke. Yeah, and this is where the standard comes in, because the standard gives you some regulation about the stroke and the decelerations involved. In fact, the buffer force is not constant. It's slightly varying, and the maximum buffer forces are slightly higher than the constant intended due to the physics of the process. So I had a look to the standards, especially EN 8120. There are different things told, and one aspect told is that you must have buffers. Very simple, at the end of a car and counterweight track. And regardless of the speed, but dependent on the speed, you can vary the type of buffer you may use. Then there are some regulations on stroke of your buffer. There's a calculation 0.067 times speed squared. They call it jump height. I have a simple experiment. This is your car driving with a speed, and I release it, and exactly the height you have seen is the jump height. And this is the minimum stroke you have seen your buffer must deliver. And because this was a deceleration with G, and the maximum deceleration in this process, medium deceleration, has to be G. What else? Strange calculations. I understood the standard is repeating itself. And there are equations at one page and other equations at another page. And if you calculate 2 or 3 pages, you realize it's the same message, no difference. And I don't know why, and it's a little bit confusing. Buffers have to be tested, type tested. There's at this test, when you calculate the decelerations, the standard gives a minimum frequency you have to use for the measurement of physical sizes. This is the time span is 0.01 second, so 10 milliseconds, which is interesting to me. Hoopsala, I missed some information which is maybe of some interest. Yes, sorry. Next to the stroke, there's some limitation on the deceleration. Not on the maximum deceleration you can put to the car, but as I say, the impulse. Decelerations larger than 2.5 G must not last longer than 40 milliseconds. So this information is given. Okay, I'm not an expert to lifts and I have no idea. And so I just took a photograph last year at the desk of colleagues. If you want to see, you can see the same buffer on the desk today. This is a buffer rated for 1 meter per second lift speed. This is a speed where you are forced to use a hydraulic buffer, and it has a stroke of 33 millimeters and is rated for a certain mass. Mass range 380 kilogram to up to whatever, we will see it. And I improved my simulation tool to adapt to the calculations needed to calculate the deceleration process for such buffers. You can see here, yeah, this is exactly this buffer, 73 millimeters stroke, about 3 tons weight, at 1 meter per second speed. The standard says you have to calculate with 15% more. And down here, unfortunately, it's not of a good quality here. You can see in blue color the force occurring, and on the right side in red color the deceleration occurring. And if you see this process in detail, the maximum deceleration is 10.4 meters per second squared. So a little bit more than g, but the medium value is below g, so everything is fine. But this is at maximum load, 3 tons. You can use the buffer also for smaller loads, 380 kilograms, and the same calculation shows that you get much higher decelerations at the peak. But you also see after 10 milliseconds of time, the deceleration is well below 2.5 G. So this buffer meets the requirements according to the standard. This was my first result. Okay, I took another example you cannot find here on a desk. But this is a buffer for lift driving at 4 meters per second speed. So 16 times the kinetic energy at same mass, but the mass is even higher. Yeah? So you have much more kinetic energy at 8 tons, the according speed, and a stroke of 1.2 meters in this case. Yeah? And you get, again, such a curve about acceleration, maximum value, somewhat above G, but not much. And the medium value is well below G. And now for the minimum rated mass, 1 ton, you get the result that you have a very high peak of deceleration, and the deceleration decreases also quite fast. But here you can see the point where the deceleration is 2.5 G, and this occurs after 45 milliseconds. So this configuration does not meet the requirements of the standard. And now you have to vary the characteristics of the buffer in order to meet the requirements. This is possible, and I've done this. And you get now changed results. Yeah? And this is with high mass, maybe not so interesting, but with lower mass, again, 1 ton, you see by the right throttle, the acceleration 2.5 G is exactly met after 40 milliseconds. So we are exactly at the border, and this would fulfill the standard. But, and now this is the interesting point for me, you can see the maximum decelerations in the original configuration was about 160 meters per second squared. 160, so about, let's say, 16 G. Yeah? And the price for this modification is that the maximum deceleration is about 250 G. This is 250 meters per second squared, 25 G. So the maximum deceleration is much, much higher if you adapt the characteristics of the buffer. And this point is not a topic in the standard at all. So you can do with your buffer whatever you want. If the maximum decelerations occur during a short time span, they can reach any level. So that's about this topic. To conclude about this measuring frequency, we speak about a requirement about lasting 40 milliseconds time. In fact, I do not understand the requirement on measuring equipment, which has to be just 100 hertz measuring frequency. You get only 2 measuring points during this process. And in fact, you have to increase the requirement to meet the standard requirement according to this measuring regime. This is one point I do not understand, and the other point I do not understand in fact, but I'm not from ergonomic side of this topic. Why is there in this standard no restriction of the maximum decelerations? They can adopt any level possible by the design, as long as it lasts a short time. That's it. Thank you very much.
Thank you very much. Any questions?
Thank you. I think just commenting on your last question, I think traditionally in the lift industry, people have always relied on measuring a distance and assuming that the deceleration within that distance was constant, and then reverting to the equation v square minus u square equals 2as. I'm not saying that that's right, but I'm just, for example, when a car stops on the safety gear, what technicians usually do, they'll go to the guide rail and they'll measure the mark, the length of the mark. Mm-hmm. And from that, they will assume that the average they're calculating basically the average acceleration rather than the maximum. I think with more tools, precise tools for measuring acceleration, that might become something that people can look at and look at the maximum deceleration. So I don't know if people agree, but I think that's my probably the best guess. Yeah. The best guess.
Mm-hmm. Thank you.
Sitting up for the next presentation with another question.
Actually, there's an assumption in lifts that if you don't exceed 1 G of the deceleration, that people won't be injured. Mm-hmm. And so that's sort of the background on safety gears, on buffers and that type of thing. So the idea is you should design your buffer or select your buffer based on never exceeding 1 G, either empty car or full car. And so that's why you have to look at not just what the maximum capacity is, but when the car is empty, what am I going to hit? And you are allowed to have some short duration transients. When you say frequency, I think you really, the more common term I'm thinking of is sample rate. And if you have a higher sample rate, if they had a higher sample rate, they would probably find more of them that don't meet the standard. And so that's my guess.
Well, due to my understanding, higher sample rate does not help to find more of these events, probably. But generally speaking, with a requirement on the medium deceleration of 1 G, there's no message about the real distribution. And the system can be designed in any way to meet the medium value. And for me, this question is not clear, if it's of any relevance at all, but are there some points not to exceed, looking on this intrinsic aspect? But maybe this is just research and solving of some differential equations, nothing more. I do not know. Yeah. Okay, thank you.
Thank you very much. Thank you.